where's the cursor? Oh,
I'll start the timing when I know you can advance.
yes. Okay. Well, we are almost at the end of the meeting, so I thought we'd have a look back at what we've heard over the couple of past days. So it was a meeting on RLR, but we heard a lot about general physics of stars. We heard obviously a lot about the pulsations, about RLR all across the Milky Way, and in dwarf galaxies, and in the bulge, and beyond. And most recently, also about the metal poor stars now, more broadly. And as after just a couple of days, I kind of ran out of real estate on my title slide. I think this really gives a testament to George's impact on the field. So George, thank you so much for getting us all here and making this a very interesting couple of days. It is also a testament of how exciting our galaxy is and how exciting it is to be studying the Milky Way and resolve stellar populations at this moment in time. And so the topic of my talk will be on how all of these pieces, different pieces, come together and interact within the Milky Way. And to do this, I will be using data from the Gaia survey, which is shown here in the background, and also the spectroscopic survey called H3. So with the Gaia just releasing like 30 million spectra on Monday, the question is like, why do we need another spectroscopic survey? Now, it turns out that Gaia spectra will only be available for stars brighter than 6 in magnitude. And so since we were interested in the halo stars, we wanted to get some spectra on stars fainter than that. So for that reason, we launched the H3 survey, which stands for Hectoshell in the Halo at High Resolution, which is a blind survey conducted on the Hectoshell instrument on MMT. We started in September 2017, and you see our targeting strategy. It's like a blind survey where we only select for stars with small parallaxes and at high galactic latitudes. And so you can see at some point we hit COVID concerns where the survey stalled a little bit, but then it picked up late last semester. And at this point, this is the coverage actually at the end of the year. So we've now have more than 220,000 stars observed in this arbiter 31 wavelength range with a resolution of 32,000, which allowed Phil Cargill, who is a postdoc who developed the survey pipeline, to measure radial velocities with precision better than 1 kilometer a second. And there is an example spectrum in black and a best fit model in purple. But these spectra are just part of the analysis. Actually, Phil is using also all the available, well, not all, but optical and infrared available broadband photometry to simultaneously solve not just for radial velocity, but all the other stellar parameters. And in particular, then that allows us to also get a sense of the distance. So the average, or no, we have distance precision for more than 90% of the stars in our sample, better than 20%. So at this meeting, like this might sound like a humble goal, like given all the nice RLR distances, but it actually beats Gaia parallaxes by a lot in the halo. And so now that we have all of this information, like both the radial velocities and the distances, means we have, for at least the sample of stars, a full set of phase space coordinates. And what that allows us to do is actually reconstruct the formation history of the Milky Way. So we think that the galaxy was born hierarchically, and when a dwarf galaxy merges onto the Milky Way, like galaxy with the position of the disk and the star showing the solar position, can in these early stages identify merging dwarf galaxies just as in spatial overdensities. However, once we have many of them and enough time has passed, like this in the spatial coordinates, this all becomes phase mixed. However, in the space of energy and angular momenta, all of these different dwarf progenitors of the Milky Way remain distinct. And obviously, like this is a simulation where the energy and the angular momentum are exactly conserved. In the Milky Way, they are not exactly, but still, this is definitely a space where the Milky Way progenitors should kind of better stick out. And to switch now on the data after a couple of years of running the H3 survey, here's work done by the Harvard graduate student, Rohan Naidu, who actually just graduated and will be moving to MIT as a Hubble and Pappalardo Fellow, showing what the H3 looks like in this similar plot. So he's showing the Z versus X positions of H3 stars on the left, and the energy angular momentum phase space diagram on the right. And as you can see already, there's like a lot of mixing, kind of where it's hard to pick out stars spatially, but even just like a casual glance on this energy angular momentum space, you might see like that most of the stars are here clustered on radial orbits of angular momentum of 0, which is the merger debris of the Gaia Sausage Enceladus dwarf galaxy. Then there's like a slight overdensity to the upper left, which is a Sagittarius dwarf galaxy. And here is this left edge is actually showing the stars of the disk that kind of entered our selection. And what Rohan did is then just a very careful analysis of this space and found that once you remove like these things you can pick out by eye and look into chemistry, you can actually assign kind of the origin of more than 85% of stars on this plane. So now I color coded all the different structures that Rohan has identified and really shows that now we can kind of completely decompose the origins of stars in the Milky Way. And this was exciting, but happened 2 years ago. We kept on going, and the idea is that we might be finding even lower mass galaxies that maybe didn't have that many stars in this initial plane. So it's been kind of my go-to diagram of like this energy angular momentum plane to see kind of how well the survey is doing. After every run, we would have an updated catalog and I would make this plot. So this is the version from April, like including data through April 2022, which was our last run. And rather than find some like new clump of a dwarf galaxy, I noticed that what appear to be like ripples over here on the disk plane. There appear to be kind of small protrusions from this edge towards more radial orbits. And so a little bit surprised of kind of where what this is, but I wanted to be more quantitative to see if they're actually significant. So here is the histogram of energies of stars singletonous higher than 5. That also includes the bootstrap of their observational uncertainties. You can see the peaks are pretty prominent. If we do the same exercise for higher signal-to-noise stars, you see that these peaks remain prominent. And kind of emboldened by the prominence of these peaks in the disk, I thought like, I kind of see peaks on this halo region of radial orbits as well. So to show those histograms as well, you can see that they actually line up pretty well. And we can see the guiding lines show the some of the gaps between these peaks that the two populations have in common. And then the question was like, what can cause this? Like it seems like it has to be something external because they appear to be like the set of values appear the same in both populations. And so another way to look at it, or to gain clues, I thought would be to look at the distribution of orbital periods for both of these populations. So I have the disk on top and halo on the bottom. And again, you see like there are many peaks. It's not a smooth distribution. And you know, it was kind of like, what could possibly do this? There are like only so many massive objects in the Milky Way. So I thought like, okay, well, let's look at Sagittarius. So here is the orbital frequency of Sagittarius on the 1-to-1 line is for this back on the right, and then the simple orbital resonances closer in. So you can see some of them at least line up with the gaps over here, which is suggestive, but not all of them. And there's, as we heard from Andrea, another massive actor in the Milky Way, the rotating bar. So here's where the Bark rotation would be. Again, kind of falls like on one of the gaps in the disk. And this is, I think, highly suggestive. I don't have the full answer to, but I wanted to end with this kind of idealized simulation of what such an interaction might look like. So I'll just briefly explain what the movie will show. So I set up a simple like infinitely thin disk that's on all stars initially on circular orbit, interacting with Sagittarius 5 billion years. And you'll see that in the inset on the upper right. And then the most of the plane will be the energy angular momentum of the simulated stars, which is on the left edge, and then the mirrored observed H3 stars on the right in the disk. So you can see like in every kind of pericentric path to Sagittarius kind of perturbs this, causes these ripples in the energy place. It's also a very dynamic picture, so it looks like it would need to do a lot of modeling to to really understand kind of what the exact positions of energy ripples correspond to. But so there's like a lot more to do both on the data side and modeling side. But I think this is super exciting. I wanted to get all of your questions and ideas of what to check for further. Thank you.
Thank you. Questions, Heather?
Just one word. You.
Thank you.
Any questions, Mike?
How do you associate these different components out of which the Milky Way is supposed to be built with this ripple picture? I mean, I'm surprised that you would have the ability without beyond, alpha and Fe, to identify so many different subcomponents out of which the Milky Way is built. And then how does that fit into this picture? I'm a little confused.
Yeah, that's a great question, and it's in a 10-minute talk I can only show so much. However, this is one thing that we did check. So in the disk, someone first asked like maybe this is like another dwarf galaxy, but the chemistry of these stars, like in these protrusions, are actually the same as the chemistry is in the disk. So this is all, and if you just select on the kind of disk, like we measure alpha element abundances as well, so alpha and iron. So if you select kind of the thick disk-like chemistries, you get basically the same diagram as just selecting like this selection of the disk stars. The situation is more interesting in this halo component. So I wrote down what my selection is there. So I just choose like very eccentric stars and on this prograde side here. So there is a mixture, and you can see it here from actually in this Rohan's image, that most of the stars in this region are from Gaia Sausage Enceladus. However, there are some of these pinker stars, which are the splash disk stars and this the kind of higher eccentricity orbits. And when we look at these two populations, they show the same pattern of energy peaks and valleys. So, which I think also argues that this is something external that has shaped both populations.
And
in
those
this
population assignments, that's discussed in the 90.
yes, exactly. Yeah.
I'm
Yeah.
quite surprised that the defined structure.
Yeah, there's a lot more that can be done, and we heard from Tim as well. This was kind of a maybe more astronomers like way of doing like hard cuts in certain like multidimensional places. So yeah, Rohan goes through all of these.
Other discussion? Was that? Okay, if not, let's thank Ana again.